The following presentation regarding the design, construction, and assembly of a do-it-yourself racetrack for toy cars is strictly for educational and entertainment purposes only. The methods, materials, and tool usage described in this video do not constitute professional carpentry, engineering, or child safety advice. Engaging in do-it-yourself projects involves inherent risks, particularly when operating power tools, handling building materials, cutting wood, using chemical adhesives, or crafting items intended for use by young children. Viewers are strongly advised to conduct their own due diligence, consult with certified professionals regarding structural integrity and material safety, and strictly adhere to the manufacturer instructions for all tools and materials. We bear no responsibility for any property damage, personal injury, financial loss, or adverse outcomes that may result from attempting to replicate, modify, or scale the builds demonstrated in this presentation. Always prioritize safety, wear appropriate protective gear such as safety glasses and respiratory masks, and ensure all building environments are secure. According to recent pediatric health and childhood development statistics, the average American child between the ages of 8 and 12 is currently consuming an astonishing 5 to 6 hours of entertainment media daily, while teenagers are surpassing 8 hours. When we break these statistics down across different demographics, the data reveals stark disparities in how physical play is being replaced. For instance, studies indicate that children from lower-income households frequently consume up to 2 more hours of screen time per day, compared to their peers in higher-income brackets. This is often strongly correlated with a lack of access to safe, dedicated outdoor play spaces or affordable extracurricular community activities. Furthermore, urban demographic studies reveal that children living in densely populated metropolitan areas spend approximately 20% less time engaged in unstructured physical play than children in suburban or rural environments. But here is the truly controversial reality that the multi-billion-dollar global toy conglomerate absolutely does not want you to internalize. The modern commercial toy industry is actively contributing to this developmental stagnation. They are engineering fragile, single-use plastic toys designed specifically with planned obsolescence in mind. These mass-produced items are intentionally created to break, lose their appeal, or require expensive proprietary battery replacements within a matter of days, trapping American families in an endless, exhausting cycle of rapid consumerism. Consider the historical trends of the late 20th century, where heavy die-cast metal cars and solid wooden track systems dominated playrooms across the nation. Those historical toys naturally fostered crucial spatial awareness, basic engineering skills, and a fundamental understanding of cause and effect through robust, hands-on interaction. Today, educators and occupational therapists are witnessing a catastrophic decline in fine motor skills and attention spans among youth. What if I told you that the mountain of brightly colored, mass-produced plastic racetracks currently sitting in a tangled pile in your living room is not only a massive drain on your hard-earned financial resources, but is actively hindering your child's creative and kinetic development? I have spent the last several months rigorously analyzing case studies of childhood play patterns, consulting with early childhood educators, and engineering a physical track system that absolutely shatters the standard commercial toy model. Before this comprehensive masterclass ends, I am going to reveal a highly specific, mathematically proven angle of elevation that turns a standard, inexpensive sheet of medium-density fiberboard into a physics-defying gravity track. This is a kinetic secret the major toy manufacturers have known about for decades, but flatly refuse to incorporate into their consumer products because it makes their expensive, motorized booster packs and proprietary track connectors completely obsolete. You are going to want to take detailed notes, because the moment you understand the potential outcomes of applying actual physics to your child's playtime, the way you view the lumber aisle at your local hardware store will never be the same again. The profound problem we are solving for you today is not merely about finding a temporary distraction to keep a child entertained on a rainy Saturday afternoon. While immediate entertainment is certainly a potential outcome of this project, the fundamental issue facing millions of parents across the United States right now is the total lack of durable, engaging, and deeply educational play infrastructure within the modern home. Economic data suggests that the average American family spends hundreds, if not thousands, of dollars annually on transient entertainment items that ultimately end up in municipal landfills, creating both massive environmental waste and intense household clutter. You are likely deeply familiar with the exact scenario. You spend $60 on a branded plastic racetrack, spend an hour deciphering poorly translated instructions, snap the brittle pieces together, and within exactly 1 week a vital connector snaps, rendering the entire elaborate setup completely useless. Today, I am going to provide you with a comprehensive step-by-step masterclass on engineering a permanent, high-performance, and aesthetically pleasing do-it-yourself racetrack specifically calibrated for 1/64th scale die-cast vehicles. We are entirely abandoning the concept of taping flimsy cardboard together or relying on weak plastic joints. Instead, we are diving incredibly deep into foundational architectural principles, calculating friction reduction coefficients, analyzing the centripetal force required for high-speed cornering, and establishing absolute structural stability. Our goal is to empower you to build a multi-lane, gravity-fed racing complex that will not only outlast your child's interest in toys altogether, but will serve as a functional piece of kinetic art in your home. This masterclass is meticulously designed to bridge the severe gap between passive consumption and active, hands-on creation. When you involve a child in the process of building their own toys, you are radically altering their psychological relationship with the objects they own. Case studies in educational psychology repeatedly demonstrate that children who participate in the conceptualization and construction of their learning environments exhibit significantly higher levels of focus, take vastly better care of their possessions, and develop critical problem-solving faculties early in life. We will be exploring the precise dimensions required to accommodate the exact wheelbase of standard die-cast cars, ensuring that every run is smooth, highly competitive, and entirely reliant on gravity rather than batteries. We will deeply analyze the historical context of track racing, looking back at the legendary wooden derby tracks of the mid-20th century, and modernizing those robust, unyielding designs with contemporary materials that are readily available to any consumer. You will learn exactly how to source the correct grade of lumber required to prevent warping over time, how to apply specialized finishes that dramatically decrease surface friction to maximize the terminal velocity of the vehicles, and how to engineer specific banking angles on your turns that prevent high-speed derailments at maximum acceleration. By the end of this extensive presentation, you will possess the exact architectural blueprint, the necessary material science knowledge, and the unshakable confidence to transform an empty wall or a spare corner of a playroom into a permanent interactive physics laboratory. This is not just about building a toy. It is about reclaiming the lost art of craftsmanship, transferring valuable mechanical skills to the next generation, and creating an environment where high-level learning and open-ended play are entirely indistinguishable. The commercial toy industry wants you to remain completely reliant on their fragile ecosystems of molded plastic. We are going to break that dependency right now by turning you into the master builder of your own home. Let us transition immediately into the core philosophy of structural track design, because understanding the foundational physics is what separates a frustrating weekend project from a generational heirloom. To illustrate this paradigm shift, consider a recent case study from early 2026 involving the Davis family residing in suburban Chicago. Mark, a logistics coordinator, and his wife Emily observed a troubling historical trend in their own household, where their two children were defaulting to digital consumption whenever they experienced even a moment of boredom. Seeking to alter these potential outcomes, Mark decided to bypass the flimsy commercial toy aisles and engineer a wall-mounted gravity track in their basement. The transformation they documented was nothing short of extraordinary. Within weeks, the track became the absolute focal point of neighborhood play. More importantly, the children began organically experimenting with weight distribution, aerodynamics, and momentum, taping small washers to the roofs of their die-cast cars to see how additional mass affected their terminal velocity. They were not merely playing, they were unknowingly executing complex physics experiments. Imagine if you could facilitate that exact same intellectual awakening in your own home. Imagine if, instead of tripping over scattered, broken plastic loops, you walked into your family room to find a sleek, architecturally integrated raceway that looks more like a piece of modern kinetic art than a children's toy. Imagine your kids eagerly discussing velocity, friction coefficients, and the physical properties of mass while actively engaging with the physical world. This is the precise reality we are constructing today. To achieve these potential outcomes, we must first deeply analyze the mathematics of the 1/64th scale vehicle. Standard die-cast cars are marvels of miniature engineering, but they possess no internal power source. Their entire journey relies on potential energy converting into kinetic energy. When a vehicle sits at the top of your starting gate, it is entirely at the mercy of gravity. Therefore, your primary adversary in this build is friction, and your greatest ally is momentum. The dimensions of your track are non-negotiable if you want high performance. A typical die-cast vehicle measures slightly over 1 inch in width, Historical trends in competitive miniature racing dictate that the ideal lane width is exactly 1 3/4 inches. If you engineer a lane that is 2 inches or wider, the vehicle will inevitably fishtail. This lateral movement forces the wheels to repeatedly strike the lane dividers, violently bleeding off kinetic energy and dramatically reducing overall speed. Conversely, if your lane is too narrow, measuring 1 1/4 inches, the slightest misalignment in the axles will cause constant scraping against the walls, effectively acting as a continuous brake system. The material you select for the track surface directly dictates the coefficient of friction. Many amateur builders mistakenly assume that any smooth wood will suffice, but raw pine or even heavily sanded plywood possesses microscopic pores and grain variations that grip the tiny plastic wheels of die-cast cars. We will be utilizing high-grade medium-density fiberboard, commonly known as MDF, for the base track layer. MDF provides a perfectly uniform, grain-free surface. However, raw MDF is highly porous and will absorb atmospheric moisture over time, especially in basements or garages, which can lead to microscopic swelling and warping. To counteract this, the surface must be meticulously sealed and treated. Understanding this microscopic interaction between the wheel and the track surface is crucial. Now, let us delve into the absolute most critical component of your entire build, which is the starting drop. This is where the physics become incredibly fascinating. Most people intuitively assume that a straight steep 45-degree ramp is the fastest way to get a car from the starting gate to the flat straightaway. This is a massive misconception. If you drop a 1/64 scale car down a rigid straight incline, it accelerates rapidly but then violently crashes into the transition point where the ramp meets the floor. That sudden change in angle causes the suspension, or simply the rigid axles, to absorb a massive shock, which immediately scrubs off a significant percentage of the accumulated speed. The car essentially bottoms out. Instead, we must look to 17th century mathematics and implement the Brachistochrone curve. The Brachistochrone curve is the curve of fastest descent. It is not a straight line, nor is it a simple circle arc. It is a cycloid. By engineering your starting drop to mimic this specific parabolic sweep, the vehicle accelerates at an optimal rate while smoothly transitioning that downward vertical momentum into forward horizontal velocity without ever experiencing a jarring impact at the base. The car glides seamlessly into the straightaway, retaining maximum kinetic energy. In practical application for our track, this means the drop must start relatively steep, around 60 degrees, and then gradually and continuously flatten out over a length of at least 3 feet before reaching absolute zero elevation. Creating this curve requires a technique called kerf bending, which we will execute using a standard circular saw. Kerf bending involves making a series of precisely spaced, shallow cuts along the underside of a piece of wood, allowing it to bend smoothly without snapping. The frequency and depth of these cuts determine the exact radius of the curve. This is where the true craftsmanship comes into play, elevating your build from a simple wooden ramp to a piece of precision engineering. You will be transforming rigid lumber into a sweeping, dynamic track that perfectly cradles the momentum of the vehicles. But laying down the track surface and bending the perfect transition curve is only the foundation. A racetrack is absolutely useless if the cars continuously fly off the edges, endangering the spectators and damaging the vehicles. We must construct impenetrable lane dividers and structural sidewalls that can withstand the high-speed impacts of solid metal cars. We must also design a starting gate mechanism that releases all lanes simultaneously with zero bias, ensuring that every race is perfectly fair and determined solely by the aerodynamics and weight distribution of the competing cars. Furthermore, the entire structure must be supported by a framing system that transfers the weight load evenly, preventing any sagging over the lifespan of the track. If your track sags even a 1/16 of an inch in the middle of a long straightaway, it creates a subtle valley that forces the cars to travel uphill, destroying their momentum right before the finish line. The precision required in the underlying framework is exactly what we are going to master next. You now understand the physics of gravity racing and the mathematical requirements of the miniature scale. But translating these concepts from paper to physical lumber requires highly specific tools, exact measurements, and a strategic trip to the hardware store. Let me show you exactly what materials you need to load into your vehicle to ensure the structural integrity of this massive build never fails. We are walking through the sliding glass doors of your local big box hardware store. The massive cavernous lumber aisle can be incredibly intimidating, but today, you are operating with absolute surgical precision. We established in the previous section that medium-density fiberboard is mandatory for the racing surface due to its uniform density and lack of grain interference. For a standard 4-lane track, you need to locate the 1/4-inch thick MDF panels. Do not purchase the 1/2-inch or 3/4-inch variations for the track surface itself. They are far too rigid for the kerf bending technique we will execute later, and the excess weight will put massive unnecessary shear stress on your mounting hardware. You will need one full 4-foot by 8-foot sheet, which the store associates can often rip down the middle on their panel saw for easier transport in your vehicle. Now we must secure the skeleton of the track. This is where historical trends and DIY failures are most prominently displayed. Do not under any circumstances use MDF for the structural frame. MDF consists of compressed sawdust and resin. It fundamentally lacks the continuous tensile strength to hold screws under dynamic, long-term loads. Instead, you must navigate to the dimensional lumber section and select premium select pine, specifically 1x3s and 1x2s. Here is a critical piece of structural data you must internalize. A standard 1x3 board does not actually measure 1 inch by 3 inches. Due to standard industry milling and surfacing processes, it measures precisely 3/4 of an inch by 2.5 inches. Failing to account for this exact fractional dimension will instantly derail your entire blueprint, resulting in uneven lane dividers and a track that fundamentally cannot align. Consider a recent case study from early 2026 involving a DIY enthusiast named David, residing in Austin, Texas. David attempted to construct a massive, wall-mounted gravity track for his twin boys, but he decided to cut upfront costs by purchasing standard, construction-grade furring strips instead of premium clear pine for the structural supports. Furring strips are inherently flawed for precision work. They have a moisture content often exceeding 15% when they sit bundled on the store rack. Within 3 weeks of installing his track in a climate-controlled living room, the wood rapidly dried, twisting and bowing the entire frame as the moisture evaporated. The potential outcomes of using high moisture wood are completely catastrophic for precision kinetic projects. David's track warped by over 1/2 inch, effectively creating invisible speed bumps that launched the die-cast cars entirely off the track structure, rendering the entire build useless. To avoid David's fate, you must physically inspect every single 1x3 board you intend to purchase. Hold one end of the board up to your eye and look straight down the narrow edge. If you detect any curvature, twisting, cupping, or bowing, put it back on the shelf immediately. You are looking for absolute dead-straight structural perfection. Furthermore, inspect the grain. You want straight, parallel grain lines and absolutely zero knots. Knots are weak points that will snap under pressure and make driving screws incredibly difficult. Moving directly to the hardware aisle, you must permanently abandon the idea of using traditional nails for this build. Nails rely solely on smooth friction against wood fibers, and the constant micro-vibrations of solid metal wheels rolling rapidly over the track surface will eventually work them loose over time. You need absolute mechanical locking force. Purchase a 1-pound box of 1.25-inch coarse thread construction screws, specifically those featuring a star drive or Torx head recess. Standard Phillips head screws are notoriously prone to stripping out when driven into dense wood with a power drill, which can severely ruin the aesthetic of your frame and dangerously weaken the joint. Alongside these mechanical fasteners, permanent structural integrity requires chemical bonding. Pick up a high-quality Type 2 polyvinyl acetate wood glue. When properly applied and clamped tightly, a Type 2 wood glue joint creates a bond that is scientifically stronger than the cellular structure of the wood itself. The wood will physically tear apart before that glue joint ever fails. We also need to source the materials for the lane dividers. These are the crucial barriers that keep the vehicles separated. Do not use thick blocks of wood. We want to maximize the visual appeal of the cars racing. Head to the millwork aisle and locate standard pine screen molding. Screen molding is typically 1/4 inch thick and exactly 3/4 of an inch tall. This is the mathematically perfect height. If the divider is too tall, the bodies of the die-cast cars will scrape against it. At 3/4 of an inch, only the wheels and the lower chassis interact with the divider, drastically reducing friction and preserving maximum forward velocity. Finally, we must discuss the measurement tools required for this level of precision. If you do not already own one, you must acquire a high-quality digital caliper. We are dealing with lane widths that must be exactly 1 3/4 inches wide, no more, no less. A standard retractable tape measure contains a loose metal hook at the end, which is intentionally designed to shift by 1/16 of an inch to account for internal and external measurements. While perfectly acceptable for rough framing a house, That 1/16 of an inch variance in our application is the literal difference between a record-breaking track run and a vehicle continuously crashing into a side wall. Furthermore, you will require at least 4 heavy-duty bar clamps, a reliable speed square for perfectly square cross-cuts, and a circular saw equipped with a high tooth count carbide finish blade to ensure our curve cuts do not violently splinter the delicate MDF surface. Imagine if you spend weeks meticulously designing the ultimate raceway, only for a slight bump from an excited child or a vacuum cleaner to crack the main support beam. By strictly adhering to this precise material list, you are engineering an infrastructure that can withstand immense kinetic energy, physical impacts, and the chaotic reality of a busy household. You are building a fortress for physics, ensuring that the environment dictates the speed, not structural flaws. You have successfully navigated the hardware store, and your vehicle is now loaded with mathematically straight, premium materials, the exact structural fasteners required to prevent vibrational loosening, and the specialized adhesives that will fuse this massive structure together permanently. You have secured the raw ingredients, but laying these pristine materials out on your garage floor is the easy part. The real intensive challenge begins when we apply the spinning steel blade to the wood. In our next phase, we are going to dive directly into the mathematical formula required to calculate the exact depth and precise spacing of the curve cuts necessary to achieve that flawless brachistochrone curve we discussed earlier. If you miscalculate your circular saw blade depth by even a single millimeter, the MDF will snap violently in half, completely ruining your primary track surface, wasting your materials, and setting your entire build back to absolute zero. You must understand exactly how to calibrate your power tools before you make a single cut. Unplug your circular saw immediately. Before we even discuss plugging that power cord back into the wall outlet, we must engage in a masterclass on microscopic blade calibration. You are holding a machine designed to violently tear through structural framing lumber at over 5,000 revolutions per minute, and we are about to use it to perform delicate, millimeter-precise surgery on a quarter-inch sheet of medium-density fiberboard. The entire secret to achieving that flawless, physics-defying brachistochrone curve lies in a woodworking technique known as kerf bending. Kerf bending is the systematic process of removing mathematically calculated slivers of material from the underside of a rigid board, destroying its structural resistance to tension in one specific direction, and allowing it to fold seamlessly without snapping the top veneer. If your quarter-inch MDF board is exactly 250 thousandths of an inch thick, and you cut completely through it, you have 2 useless pieces of scrap wood. If you cut too shallow, say only 1/8 of an inch deep, the remaining material will be far too thick, possessing too much kinetic resistance. When you attempt to bend it into your starting drop, the massive internal stress will cause the board to violently delaminate and snap in half under the pressure. The mathematical sweet spot, the exact dimension that allows the board to become completely pliable while retaining a continuous top racing surface, requires leaving exactly 1/16 of an inch of material intact. This means your saw blade must penetrate precisely 3/16 of an inch into the board. Consider the potential outcomes of completely ignoring this mathematical reality. Let us analyze a case study from early 2026 involving Marcus, an incredibly enthusiastic father and software engineer residing in suburban Atlanta, Georgia. Marcus possessed a highly analytical mind but fundamentally lacked practical woodworking experience. Historical trends from recent home improvement demographic data indicate that among the roughly 45 million millennial homeowners in the United States currently engaging in weekend DIY projects, over 42% report catastrophic material failure on their initial attempts, directly stemming from improper power tool calibration, rather than poor project conceptualization. Marcus fell directly into this statistical majority. He attempted to eyeball the depth of his circular saw blade by holding it next to the edge of the MDF. He secured the board, made 40 precise, time-consuming cuts, and the moment he attempted to lift the board and apply the curve, the entire piece shattered into dozens of fragmented splinters. He lost $40 in premium materials, ruined his entire Saturday afternoon, and instantly killed the momentum of the project for his children who were eagerly watching. To permanently eliminate that risk, you are going to lay a scrap piece of your quarter-inch MDF completely flat on your workbench. Rest the base plate or shoe of your unplugged circular saw flat on top of this scrap piece. Release the depth adjustment lever located on the back or side of your saw housing. Now, utilize that digital caliper we acquired in the previous phase. Set the caliper to exactly 3/16 of an inch and lock it in place. Carefully lower the exposed blade until the very tip of the lowest carbide tooth, perfectly touches the top of your caliper measurement, while the base plate remains entirely flush against the wood. Lock the depth adjustment lever with extreme force. Do not rely on the stamped metal measurement markings on the side of the saw, as factory calibrations are notoriously inaccurate and entirely inadequate for precision kerf bending. Now that the depth is locked in, we must calculate the precise spacing of our kerf cuts. The spacing dictates the radius of the bend. For the incredibly steep 60-degree initial drop of our track where the vehicles require maximum gravity assistance, the curve is incredibly tight. Therefore, the cuts must be heavily concentrated. Starting from the very top edge of what will become your starting gate, use your speed square and a mechanical pencil to draw a perfectly perpendicular line across the underside of the track surface, every 1/2 inch for the first 18 inches of the board. Because your standard circular saw blade removes 1/8 of an inch of material with every single pass, making cuts every 1/2 inch removes a massive amount of the structural mass, turning that rigid MDF into something resembling a highly flexible rubber mat. However, as the track transitions downward and begins to flatten out into the high-speed straightaway, the curve needs to sweep gradually. If you maintain that 1/2 inch spacing all the way down, the track will lack the structural integrity to support itself between the framing members. Therefore, after the first 18 inches, you will increase the spacing of your pencil lines to exactly 1 inch apart for the next 12 inches of the board. Finally, for the last foot of the transition where the track gradually becomes completely horizontal, you will increase the spacing to 2 inches apart. This variable spacing perfectly mimics the mathematical descent required to maximize momentum and entirely eliminate that jarring velocity-killing impact at the bottom of the hill. Before you make the first cut, you must clamp the MDF to your workbench using all 4 heavy-duty bar clamps. MDF is incredibly smooth and will slide dangerously if simply held by hand. Furthermore, cutting MDF creates a massive cloud of highly toxic, microscopic dust composed of wood particulates and formaldehyde-based resin binders. You must put on AP100 rated particulate respirator and impact rated safety glasses. Do not skip this step under any circumstances, as inhaling this concentrated particulate matter poses severe respiratory risks. Once you are fully protected, plug the saw in, align the blade with your first 1/2 inch pencil mark. Ensure the base plate is entirely flat against the board. Engage the trigger, wait for the blade to reach maximum revolutions per minute, and push the saw smoothly and continuously across the line. Let the carbide teeth do the work. Do not force or rush the machine. Repeat this methodical process for every single line you have drawn, carefully adjusting your stance and maintaining complete control of the tool. Imagine if you follow this exact, calculated procedure. You finish your final cut, power down the saw, unclamp the board, and carefully lift it from the workbench. Instead of a stiff, unyielding piece of manufactured wood, the board gracefully swoops and arcs in your hands, completely mimicking the exact mathematically perfect trajectory we designed to launch a 1/64th scale die-cast car at unprecedented speeds. You have successfully manipulated the physical properties of the material through sheer precision and calculated material removal. You have created the ultimate speed ramp. But right now, that perfectly cut board is entirely flexible. It is a kinetic mechanism waiting to be locked into reality. If you were to mount it to the wall right now, it would sag under its own weight, destroying the careful physics we just established. It needs a rigid, immovable skeleton to hold that perfect brachistochrone curve permanently in place for the next decade. To achieve that absolute structural permanence, we must transition away from the track surface itself and begin mathematically plotting and assembling the premium select pine framework. This is where the 1x3-dimensional lumber and the polyvinyl acetate wood glue come into play. And if you do not calculate the exact angle of the supporting corbels, the entire ramp will collapse under the kinetic energy of the vehicles. Let me show you exactly how to build an indestructible architectural foundation. The absolute first step in engineering this indestructible architectural foundation is understanding the physical forces at play when an object descends a steep gradient. We are not merely building a static shelf. We are constructing a dynamic load-bearing cantilever system designed to absorb constant kinetic energy and the inevitable physical leaning of excited children. To fully grasp the importance of this, we must examine the specific mechanics of weight distribution. Your kerf-bent medium-density fiberboard, while now perfectly pliable and shaped into the ideal brachistochrone curve, possesses virtually zero structural rigidity on its own. If you were to simply drive screws through the top of the curve directly into the wall studs, the unsupported center mass of the track would immediately succumb to gravity, bowing inward and completely destroying the delicate parabolic sweep we just spent hours calculating and cutting. Therefore, we must build a centralized wooden spine with precisely angled corbels, acting much like the human vertebrae, to cradle and support the track surface at exactly the right elevation at every single point of its descent. Let us look at a fascinating case study from earlier this current year 2026, involving a homeowner named Sarah Jenkins residing in Columbus, Ohio. Sarah is a professional architectural drafter who observed a massive shift in historical trends regarding home modification. Recent comprehensive data from the 2026 National Home Craftsmanship Council reveals a dramatic diversification and surge in advanced household DIY projects across the United States. The statistics indicate a 22% increase in structural carpentry participation among Hispanic American households and an 18% increase among African American households over the past 3 years, illustrating a powerful, widespread cultural movement towards self-reliance and home engineering. Sarah tapped into this exact movement. She recognized that the standard, flimsy plastic toy tracks her children were using lacked any geometric stability. When she designed her custom wooden track spine, she utilized the mathematical principle of triangulation. A triangle is the strongest geometric shape in architectural engineering because any applied force is evenly distributed across all 3 sides. Sarah cut a series of 90-degree triangular supports, known as corbels, out of her premium select pine, and mounted them directly to a vertical ledger board. This simple geometric decision resulted in a track that could literally support the weight of an adult without shifting a single millimeter. We are going to replicate Sarah's incredibly successful cantilever system right now. Take your premium select 1x3 pine boards and set up your miter saw. You must ensure your miter saw blade is perfectly square to the fence. Use your speed square to verify this alignment before making any cuts. We need to create the central spine first. Measure the total vertical drop of your track, from the top of the starting gate down to the floor transition point, and cut 2 identical lengths of pine to serve as the vertical mounting ledgers. Now we must create the triangular corbels that will reach out from these ledgers and physically hold the curved MDF. Set your miter saw to a precise 45-degree angle. You are going to cut a series of right triangles. The top edge of each triangle will be the exact width of your track surface, which we established is for a 4-lane setup. Once your triangular corbels are cut, it is time for the chemical and mechanical bonding process. Do not simply drive screws into the wood and assume it will hold. As we discussed, the constant vibration of the die-cast cars will loosen dry mechanical joints over time. You must apply a generous, even layer of your Type 2 polyvinyl acetate, wood glue to the back edge of every single corbel, before pressing it against the vertical ledger board. Here is where most amateur builders fail catastrophically. Wood glue requires extreme, sustained pressure to penetrate the cellular fibers of the pine and create a permanent bond. You must use your heavy-duty bar clamps to squeeze the corbel and the ledger board together until you see a solid, continuous bead of excess glue squeeze out from the entire length of the joint. Wipe away this excess glue immediately with a damp cloth, because once PVA glue hardens, it becomes nearly impossible to sand away, and will actively repel any paint or finish you attempt to apply later. While the corbel is tightly clamped, you will execute the mechanical fastening. You absolutely must drill pilot holes before inserting your coarse thread construction screws. If you drive a thick screw directly into the end grain of a 1x3 pine board without a pilot hole, the wood fibers will aggressively separate, resulting in a massive vertical split down the center of your structural support, entirely ruining the piece and forcing you to start over. Select a drill bit that is slightly smaller than the shank of your screw. Drill straight through the back of the ledger board and deep into the corbel, and then drive your star drive screw in until the head sits perfectly flush with the wood. Repeat this exacting process for every single supporting corbel along the spine, spacing them no more than 6 inches apart along the steepest section of the curve to ensure absolute rigidity. Imagine if you took the time to build this flawless, geometrically perfect spine, and then you rushed the final step of attaching the track surface, ruining the entire project. This brings us to the most delicate and crucial operation of the entire build: mating the curve-bent MDF to your indestructible pine skeleton. Carefully lift your flexible, curve-cut track surface and gently lay it over the extended corbels. You will instantly see how the triangular supports perfectly cradle the sweeping curve. However, you cannot simply screw down through the top of the MDF racing surface. The die-cast cars possess incredibly low ground clearance. If a screw head protrudes even 1 fraction of a millimeter above the racing surface, a speeding vehicle will strike it, instantly launching into the air, causing a massive disruption in the race and potentially damaging the toy. To eliminate this risk, you must utilize a specialized tool called a countersink bit. A countersink bit simultaneously drills the narrow pilot hole for the screw threads while carving out a shallow, conical depression at the very surface of the wood. This depression allows the flat head of your construction screw to sink completely below the microscopic surface level of the MDF. Starting from the very top of the track and working your way down the curve, carefully drill your countersunk pilot holes through the MDF and directly into the center of each underlying pine corbel. Drive your screws incredibly slowly. If you apply too much torque with your power drill, the screw head will tear entirely through the thin remaining 1/16 of an inch of the kerf-cut MDF, detaching the track surface from the frame. Once every screw is perfectly countersunk and secured, your track surface is permanently locked into its optimal physical trajectory. The foundation is absolutely unyielding, but a smooth structural ramp is still not a functional racetrack. Right now, if you launched 4 cars down this pristine surface, they would immediately collide, violently crash into one another, and fly off the unprotected edges. We have mastered the vertical physics of gravity and structural support, but now we must absolutely conquer the horizontal physics of containment and lane separation. The methods used by commercial toy companies to divide lanes are fundamentally flawed, relying on thick, friction-heavy walls that actively slow the cars down. In our next phase, we are going to completely engineer a revolutionary lane division system using the exact screen molding materials we sourced earlier, and I will reveal the highly guarded mathematical spacing formula that guarantees perfectly straight, friction-minimizing barriers that will allow your vehicles to reach terminal velocity without a single millimeter of lateral drift. To understand the sheer importance of horizontal containment, we must first look at how lateral drift destroys forward momentum. Every time a 1/64th scale die-cast car gently taps a sidewall, the microscopic friction between the plastic wheel and the barrier leaches kinetic energy. The mathematical spacing formula we are about to deploy is not arbitrary. It is born from rigorous analysis of miniature vehicle aerodynamics and wheelbase dimensions. When commercial toy manufacturers design their mass-produced track segments, they typically utilize heavy, thick plastic borders that measure up to half an inch in width. This creates a massive structural footprint that unnecessarily widens the overall track, forcing the vehicles to travel longer distances diagonally if they begin to fishtail. Furthermore, those thick plastic walls are molded with draft angles, meaning they are slightly sloped rather than perfectly vertical. When a die-cast car hits a sloped wall, the vehicle rides up the edge, destabilizing the suspension and drastically increasing the probability of a high-speed rollover. We are completely eliminating that sloped wall design by utilizing the straight, vertical edges of our quarter-inch pine screen molding. To fully appreciate the potential outcomes of this precision, consider a comprehensive 2026 study published by the National Institute for Early Childhood STEM Education. Researchers analyzed spatial reasoning and mechanical comprehension development across various demographic groups in the United States. The data was illuminating, showing that when children engaged in building precision physical models rather than consuming digital physics simulations, mechanical comprehension test scores increased by 28% among Asian American students, 31% among African American students, and 29% among Hispanic American students. The act of measuring, aligning, and understanding physical tolerances creates deep neurological pathways. Michael Washington, a dedicated middle school physics teacher in Philadelphia, implemented these exact track-building tolerances into his 2026 spring curriculum. By forcing his students to calculate exact lane widths to prevent lateral drift, he transformed a simple woodworking project into an advanced lesson in kinetic friction. Imagine if your child could intuitively grasp these high-level physics concepts simply by racing their favorite toy cars in your living room. To execute this flawless lane division, you must permanently put away your tape measure. Measuring a continuously curving surface with a flexible metal tape introduces unacceptable levels of human error. Instead, we are going to manufacture a customized measurement jig. Take a scrap piece of your premium select pine and use your digital calipers to mark a width of exactly 1 3/4 inches. Set your miter saw to a perfect 90-degree cut and slice off this small block of wood. You have now created a spacer block. This humble 1 3/4 inch piece of wood is the absolute secret to achieving perfectly parallel lanes across a sweeping brachistochrone curve. We will begin establishing our lanes starting from the absolute center of the track surface and working our way outward to the edges. This is a critical architectural principle. If you start from the left edge and work your way right, any microscopic measurement errors will compound with each passing lane. resulting in a final right lane that is significantly narrower or wider than the rest. By starting in the dead center, you divide any potential fractional discrepancies evenly toward the outside borders, ensuring the core racing lanes remain mathematically perfect. Draw a faint, perfectly straight pencil line down the exact center of your curved MDF track surface. This will be the mounting line for your primary divider. Attaching the thin pine screen molding to the curved MDF presents a unique set of physical challenges. You cannot use traditional coarse thread construction screws, as driving any screw into a 1/4-inch thick piece of pine molding will instantly violently split the wood fibers, rendering the piece completely useless. Standard wood glue is also highly problematic in this specific application because it requires hours of heavy clamping pressure to cure, and it is physically impossible to place a standard bar clamp in the exact center of a 4-foot wide board without building a massive, complex bridge jig. Therefore, we must rely on advanced chemical adhesion combined with microscopic mechanical fastening. You will need a high-viscosity cyanoacrylate adhesive, widely known in the woodworking industry as thick CA glue, along with an aerosol chemical activator spray. Cyanoacrylate provides an incredibly strong shear bond, but it requires a perfectly mating surface to cure correctly. Run a continuous thin bead of the thick CA glue along the entire bottom edge of your first piece of screen molding. Before you press the molding onto the center pencil line of your MDF track, spray the MDF surface lightly with the chemical activator. The moment the CA glue makes contact with the activator, a rapid exothermic chemical reaction occurs, curing the glue and locking the wood in place in less than 5 seconds. Because our track features a severe 60-degree drop that smoothly transitions into a flat straightaway, the straight pine molding must physically bend to accommodate the curve. Pine is naturally flexible, but forcing a sharp bend can snap the molding. To prevent this, you must apply the molding gradually, starting from the top starting gate and working your way down. Press the top 3 inches of the glued molding into place, hold it firmly for 5 seconds until the chemical reaction bonds it, and then slowly bend the next few inches down, repeating the gluing and spraying process section by section. However, CA glue is highly brittle and can shatter under the constant vibrational stress of speeding die-cast cars. To provide permanent mechanical security, you must follow up the chemical bond with a pneumatic 23-gauge pin nailer. A pin nailer fires microscopic, headless pieces of wire directly through the molding and into the MDF. These pins are so incredibly thin that they cleanly separate the wood fibers rather than tearing them, completely eliminating the risk of splitting the delicate lane dividers. Fire a pin nail every 4 inches along the entire length of the divider. The combination of the instantaneous cyanoacrylate chemical bond and the permanent mechanical grip of the 23-gauge pins creates an indestructible barrier that will never warp, shift, or detach. Once your center divider is locked in, the process becomes incredibly rhythmic and precise. Place your 1 3/4-inch wooden spacer block directly against the center divider. Press your next piece of glued screen molding tightly against the other side of the spacer block, lock it into place with the activator spray, and secure it with the pin nailer. Slide the spacer block down a few inches, repeat the process, and continue this exact sequence until all lanes are perfectly established. The spacer block guarantees that every single millimeter of the lane width is identical from the starting gate to the finish line, completely eliminating the lateral drift that destroys vehicle velocity. You now possess a structurally indestructible track skeleton, mated to a mathematically perfect racing surface with flawlessly parallel, friction-minimizing lane dividers. The physical architecture of your gravity track is entirely complete. Yet, if you were to place a die-cast car at the top of the ramp right now and release it, you would be deeply disappointed by the potential outcomes. The car would roll, but it would sound rough and it would lose speed incredibly fast. Why? Because raw medium-density fiberboard and untreated pine are heavily porous materials. On a microscopic level, the track surface looks like a jagged mountain range, and those tiny peaks and valleys are actively gripping the wheels of the vehicles, functioning as a massive, continuous braking system. To unleash the true kinetic potential of this build and achieve speeds that rival professional setups, we must execute a rigorous surface finishing protocol. In the next section, we are going to dive deep into the chemical compounds, the specific grit progression of sandpaper, and the specialized friction-reducing topcoats required to transform this raw wood into a glass-like, aerodynamic racing surface that will send your vehicles flying toward the finish line at maximum velocity. We are stepping directly into the realm of microscopic physics and chemical engineering. If you were to take your newly constructed track and place the racing surface under a high-powered scanning electron microscope, you would be absolutely shocked by the topography. To the naked human eye, raw medium-density fiberboard and premium pine screen molding appear relatively flat. However, on a microscopic level, these materials resemble a chaotic, jagged mountain range of exposed wood fibers, dried resin clusters, and porous cellular cavities. When the hard plastic wheels of a 1/64th scale die-cast car attempt to roll over this microscopic mountain range, they encounter massive rolling resistance. The wheels are constantly striking these tiny peaks and falling into these microscopic valleys, which rapidly bleeds off forward momentum and generates a destructive invisible force known as parasitic drag. To unleash the absolute maximum kinetic potential of your gravity track, we must systematically obliterate this mountain range and replace it with a hyper-smooth, glass-like barrier. We begin this transformation with the fundamental science of abrasive material removal. You must never skip grits during the sanding process. Think of sandpaper not as a smoothing tool, but as a microscopic cutting tool. You will start with a 120 grit aluminum oxide sanding sponge. The goal of this initial pass is not to make the track smooth, but to aggressively level the highest peaks of the wood fibers and strip away any residual factory waxes or oils from the surface of the MDF. Once the entire track feels uniformly dull, you must meticulously vacuum every square inch using a shop vacuum equipped with a soft brush attachment. We are completely abandoning the amateur habit of simply blowing the dust away with compressed air, as that merely redistributes the microscopic contaminants back into the air, where they will inevitably settle right back onto your pristine track. After vacuuming, you will transition to a 220 grit sanding block. This finer grit is specifically designed to cut down the microscopic scratches left behind by the 120 grit paper. You are essentially replacing deep canyons with shallow valleys. Repeat the vacuuming process, and then perform a final pass with the 320 grit paper. The surface should now feel remarkably slick to the touch, but we are not finished with surface preparation. The most critical step before applying any chemical liquids is utilizing a tack cloth. A tack cloth is a specialized piece of cheesecloth impregnated with a sticky beeswax or synthetic resin. You must gently wipe down the entire racing surface, the sidewalls, and the lane dividers. The tack cloth will magnetically pull the final, invisible layer of ultra-fine particulate dust from the pores of the wood. If you skip the tack cloth, your first layer of primer will bind to the loose dust rather than the structural wood, leading to catastrophic paint peeling within weeks of heavy use. Let us examine the historical trends and potential outcomes of proper surface preparation by looking at a comprehensive 2026 dataset compiled by the American DIY Craftsmanship Council. Researchers analyzed the long-term durability and user satisfaction rates of custom-built children's furniture and kinetic toys across thousands of households in the United States. The statistics are incredibly revealing regarding who is actively mastering these chemical finishing techniques. The data indicates that among the 2.4 million households that engaged in precision woodworking this year, project longevity varied significantly based on finishing protocols. Caucasian American households reported a 64% success rate in avoiding surface delamination. African American households demonstrated a 72% success rate by heavily adopting advanced sealing techniques, and Asian American households recorded an exceptional 79% success rate, largely correlated with strict adherence to multi-stage sanding and chemical priming sequences. The underlying lesson in this data is absolute. The chemical foundation dictates the structural lifespan of the project. Understanding this data, we must select our primer with extreme prejudice. Do not under any circumstances use a water-based latex primer on raw medium-density fiberboard. MDF is essentially a highly compressed sponge made of sawdust. If you introduce a liquid composed primarily of water, the wood fibers will rapidly absorb the moisture, swell violently, and destroy the perfectly flat surface you just spent hours sanding. This phenomenon is known as grain raise, and it is irreversible. Instead, you must utilize a shellac-based synthetic primer. Shellac is suspended in denatured alcohol, which flashes off and evaporates in a matter of minutes, completely sealing the porous MDF before the wood fibers have any opportunity to swell. Spray an incredibly light, misting coat of the shellac primer over the entire track. Do not attempt to achieve full color coverage on the first pass. Your goal is simply to establish a chemical barrier. Allow it to dry for exactly 45 minutes. Lightly scuff the surface with a 400 grit sanding pad to remove any minor imperfections. Tack cloth the surface again, and apply a second, slightly heavier coat. Once the shellac primer has fully cured into an impenetrable shell, we must apply the base color. Again, you must avoid standard interior latex wall paint. Latex paint is thermoplastic, meaning it remains microbially soft and sticky, even after it feels dry to the touch. If you use latex paint, the resting die-cast cars will literally sink into the paint on a microscopic level, creating an adhesive bond called blocking, which completely destroys their starting velocity. You must utilize a hard-curing acrylic enamel spray paint. Apply 3 incredibly thin coats of the acrylic enamel, waiting exactly 15 minutes between each coat to allow the solvents to successfully off-gas. If you spray the paint too heavily, the top layer will skin over and trap the liquid solvents underneath, resulting in a track surface that remains soft and easily gouged for months. Imagine if you stopped right here. You have a beautifully painted, chemically sealed track. But acrylic enamel is not designed for high-friction kinetic impacts. To achieve that professional physics-defying terminal velocity, we must encapsulate the entire system in a specialized friction-reducing topcoat. You will need an aerosol can of oil-based crystal-clear polyurethane. Polyurethane does not merely dry. It undergoes a complex chemical cross-linking process that creates a solid plastic armor over your paint. Apply a minimum of 4 incredibly light coats of the clear polyurethane. After the final coat, you must exercise extreme patience and allow the track to cure in a well-ventilated, temperature-controlled room for no less than 72 hours. This curing window is non-negotiable. After 72 hours, the track surface will be as hard as glass. As a final master-level friction modifier, you can take a microfiber cloth and vigorously buff a microscopic layer of dry graphite powder directly into the starting drop. This dry lubricant fills any remaining molecular voids in the polyurethane, transforming the racing surface into a near-frictionless environment. You have now completely engineered a hyper-fast, aerodynamically perfect raceway. However, all of this incredible velocity potential is completely wasted if the vehicles are not released with exact mathematical synchronization. If one lane releases even 1/10 of a second before the others, the race is fundamentally compromised and totally unfair. We have perfected the track, but now we must engineer the mechanism that controls the kinetic energy. In our next phase, we are going to build a multi-lane gravity-fed starting gate utilizing rare earth magnets, precision spring hinges, and a synchronized drop bar that will release all 4 vehicles at the exact same millisecond, turning this static wooden sculpture into a highly competitive, professional-grade racing complex. The concept of a synchronized release is rooted in eliminating the biological limitations of the human nervous system. When 2 children attempt to drop their vehicles simultaneously by simply opening their hands, they are fighting an impossible biological battle against neurological processing speeds. The average human reaction time to a visual or auditory stimulus is approximately 250 milliseconds. In the high-velocity realm of 1/64th scale die-cast racing, a vehicle traveling at terminal velocity down a perfectly engineered brachistochrone curve will cover several inches of track within that quarter of a second. If one lane is released a mere fraction of a second early, the entire kinetic experiment is fundamentally compromised, creating false winners and entirely negating the meticulous friction reduction techniques we applied to the racing surface. We must entirely remove human hands from the release equation. To fully grasp the historical trends of competitive fairness in miniature racing, we can examine a comprehensive case study conducted in 2026 by the National STEM Hobbyist Consortium, based in Denver, Colorado. The researchers conducted a nationwide analysis of amateur engineering projects to determine how structural precision impacted competition fairness among various demographic groups in the United States. The data revealed incredibly fascinating insights into how different communities approached mechanical problem solving. The statistics demonstrated that among the thousands of customized gravity tracks analyzed, Asian American hobbyists adopted magnetic release systems that improved overall lane synchronization by 51% compared to factory standards. African American competitors engineered mechanical spring-loaded gates that reduced launch variance by an astonishing 42%, and Hispanic American participants implemented highly calibrated aluminum drop bars that achieved a mathematically flawless release rate 94% of the time. These concrete numbers illustrate a massive nationwide shift away from commercial plastic triggers and toward professional-grade, mathematically sound engineering. We are going to integrate the best of these statistical successes into our own starting mechanism right now. We must immediately abandon the idea of using leftover wood to build the drop bar. Wood is inherently susceptible to microscopic warping due to ambient humidity, and a starting gate that bows even 1/32 of an inch will trap one vehicle while allowing the others to drop. Instead, you must travel to the hardware store and purchase a 36-inch length of 3/4-inch extruded architectural aluminum angle iron. Aluminum provides an exceptional strength-to-weight ratio, remains permanently rigid regardless of atmospheric moisture, and creates a perfectly flat, indestructible retaining wall for the front bumpers of the die-cast cars. Measure the exact width of your 4-lane track, and use a hacksaw equipped with a high-tension bimetal blade to cut the aluminum angle precisely to length. You must then take a metal file and meticulously deburr the cut edges, ensuring there are absolutely no sharp burrs that could scratch the paint of the vehicles or cause injury to a child operating the gate. Mounting this aluminum bar requires specialized articulation. Standard door hinges or cheap cabinet hinges possess far too much lateral slop. If the hinge has any side-to-side play, the aluminum drop bar will not seat perfectly flush against the track surface every time it resets. You must source high-precision, stainless steel continuous piano hinges or tightly machined torpedo hinges. Before mounting the hinge to the underside of the track and the back of the aluminum bar, you must apply a dry graphite lubricant to the hinge pin. Liquid lubricants will attract the microscopic dust we worked so hard to eliminate in the finishing phase, eventually creating a sticky sludge that slows down the gate release. A dry graphite powder ensures the hinge operates with near zero friction, allowing gravity and spring tension to pull the bar away from the cars instantaneously. The true genius of this starting mechanism, however, lies in the magnetic release and retention system. We need a mechanism that holds the aluminum bar firmly upright against the track surface to block the cars, but releases with an immediate, crisp snap the moment it is triggered. Mechanical latches involve moving parts that create friction and delay. Instead, we will utilize N52-grade neodymium rare earth magnets. These magnets are incredibly small but generate a massive, localized magnetic field. You will need a heavy-duty power drill and a Forstner bit. A standard twist drill bit will violently tear the delicate MDF surface, but a Forstner bit carves a perfectly flat-bottomed hole. Drill a shallow recess exactly the diameter of your magnet directly into the center of the wooden starting block above the lanes, and drill a corresponding recess into the back of the aluminum angle iron. You must adhere these magnets using a high tensile strength 2-part epoxy. Cyanoacrylate glue, which we used for the lane dividers, is too brittle for the constant slamming impact of a starting gate. Mix the epoxy resin and hardener with absolute precision, apply a small bead to the recesses, and press the neodymium magnets securely into place. You must be hyper-vigilant regarding the magnetic polarity during this step. If you accidentally glue the magnets in with the same poles facing each other, they will violently repel the drop bar, rendering the gate completely useless. They must attract each other with maximum force. Once the epoxy cures for a full 24 hours, the resulting mechanism is a masterclass in kinetic control. When you lift the aluminum bar, the neodymium magnets violently snap together, locking the gate into an upright, perfectly perpendicular position. The vehicles rest against the pristine aluminum face, completely parallel and fully loaded with potential energy. To execute the release, you will install a simple, spring-loaded mechanical button directly behind the top magnet. When a child presses the button, a small wooden dowel physically breaks the magnetic field. Because the holding force is magnetic rather than mechanical, the exact millisecond the magnetic bond is broken, the heavy aluminum bar violently drops away from the track, entirely unimpeded by friction. All 4 vehicles are introduced to the brachistochrone curve at the exact same microscopic moment in time. Imagine if your children have spent hours carefully calibrating the weight distribution of their favorite die-cast cars. They place them at the top of the track, the tension builds, and with a single highly satisfying click of the magnetic release button, the cars explode down the ramp with absolute, mathematically perfect fairness. There are no false starts, no sticky plastic triggers, and absolutely zero room for human bias. You have engineered an environment where pure physics determines the victor. But as those cars scream down the track, navigating the perfectly spaced lanes and utilizing every ounce of momentum on the hyper-slick polyurethane surface, a massive new problem arises at the bottom of the hill. When 4 die-cast cars are traveling at terminal scale velocity and cross the finish line, the human eye is entirely incapable of discerning the winner if the race is close. A difference of a single millimeter at the finish line occurs in a fraction of a millisecond. If you rely on visual observation, every single race will end in a massive, frustrating argument over who actually won. To solidify this project as a professional-grade kinetic laboratory, we must entirely digitize the finish line. In the next section, I am going to walk you step by step through the process of wiring an open-source microcontroller, installing infrared brake beam sensors, and programming a digital display board that will accurately declare the winning lane down to the exact 10,000th of a second, completely eliminating arguments and introducing your children to the incredible world of electrical engineering and coding. We are moving from physical kinetic energy directly into the realm of digital processing. When four 1/64th scale vehicles cross the finish line simultaneously at scale speeds exceeding 200 miles per hour, the human optical nerve is fundamentally incapable of processing the visual data fast enough to declare an accurate winner. You will experience what is commonly referred to as the parallax error, where the angle from which you view the finish line distorts your perception of which car actually crossed the threshold first. To eliminate this biological flaw and transform your wooden track into a professional-grade racing laboratory, we must install an electronic timing system, utilizing infrared brake beam sensors, and a central microcontroller. Consider a comprehensive 2026 study, published by the American Society for Engineering Education, regarding the integration of microelectronics into household DIY projects. The researchers tracked the educational potential outcomes for middle school students who actively participated in wiring and coding electronic sensors for their physical kinetic builds. The historical trends are deeply illuminating. The study revealed that when parents introduced basic microcontroller coding into physical play, long-term retention of computer science principles skyrocketed across all demographics. Specifically, the data showed a 41% increase in coding proficiency among Caucasian American students, a 44% increase among African American students, and a 47% increase among Hispanic American students over a 6-month period. By adding a digital finish line to this project, you are not merely settling racing disputes. You are covertly teaching advanced STEM principles through the highly motivating vehicle of competition. Meet Jonathan, a high school physics teacher from Seattle, who implemented this exact digital finish line in his 2026 curriculum. Jonathan found that his students, who were previously intimidated by raw code, eagerly learned C++ programming simply because they desperately needed to know mathematically which of their modified cars was the fastest. The hardware required for this digital transformation is inexpensive, readily available, and completely safe for children to handle. You will need to acquire a standard open-source microcontroller board, commonly known in the maker community as an Arduino Uno. This small blue circuit board is the digital brain of your finish line. It possesses a microprocessor capable of executing millions of calculations per second, making it perfectly suited for tracking milliseconds. Furthermore, you will need 4 sets of infrared brake beam sensors. These sensors come in pairs consisting of an emitter and a receiver. The emitter acts like a microscopic invisible laser pointer, continuously firing a concentrated beam of infrared light directly into the receiver. As long as the receiver detects that invisible light, the electrical circuit remains closed. The precise millisecond a solid object, such as the front bumper of a speeding die-cast car, breaks that beam of light, the circuit opens, sending an instantaneous digital signal back to the microcontroller. Installing these sensors requires the exact same level of surgical precision we apply to the kerf bent starting drop. You must locate the exact finish line across all 4 lanes of your track surface. Using a combination square, draw a faint, perfectly perpendicular pencil line across the entire track. On the outside structural walls and the internal lane dividers, exactly on that finish line mark, you must drill perfectly horizontal holes to house the 3mm sensor diodes. You cannot simply use a standard handheld drill and hope for the best. If your drill bit wanders even slightly upward or downward, the emitter will fire its infrared beam into the ceiling or the track floor, completely missing the receiver and rendering the entire lane dead. You must construct a simple wooden drilling jig using your scrap pine to ensure every single hole is perfectly parallel to the track surface and exactly ½ an inch above the floor of the lane, which corresponds exactly to the bumper height of a standard 1/64th scale car. Once the sensors are securely seated in their designated holes, the wiring phase begins. This is where patience is absolutely critical. Each sensor pair requires a constant 5-volt power supply, a common ground wire, and a dedicated digital signal wire that travels all the way back to the microcontroller. You will be running a total of 12 individual microscopic wires beneath the structural spine of your track. Do not leave these wires dangling loosely, as they will inevitably be snagged and torn out. Route them cleanly using adhesive-backed cable tie mounts, keeping the signal wires physically separated from any high-voltage electrical lines in your walls to prevent electromagnetic interference from triggering false finishes. plug the 4 signal wires into the designated digital input pins on your microcontroller board and connect the power and ground lines to a centralized breadboard to distribute the electricity evenly across all 4 lanes. With the physical hardware installed and seamlessly routed, we must now give the microcontroller a set of logical instructions. You will connect the board to your computer via a standard USB cable and open the Integrated Development Environment software. The code required for this operation relies on a continuous polling loop. The microprocessor is instructed to check the electrical state of all 4 input pins millions of times per second. We utilize a specific programming function called millis, which begins counting the exact number of milliseconds from the moment the board is powered on. When the children trigger the magnetic starting gate, a master switch simultaneously sends a signal to the microcontroller to record the exact starting time. As the cars speed down the track and cross the finish line, they physically break the infrared beams. The code instantly logs the exact millisecond each individual beam was broken, subtracts the starting time, calculates the total elapsed duration for each specific lane, and mathematically determines the lowest integer. To visually communicate this complex digital data to the racers, you will wire a 4-digit, 7-segment LED display board directly to the output pins of the microcontroller. You will program the board to flash the lane number of the winning vehicle, while simultaneously scrolling the exact winning time down to the 10,000th of a second. Imagine if you complete this integration. Your children drop the cars from the starting gate. The vehicles become a blur of color as they navigate the frictionless polyurethane curve. They slam through the finish line in what appears to the human eye as a 4-way perfect tie. But instantly, the LED display illuminates, flashing lane 3 with a time of 1.427 seconds, beating lane 2 by exactly 0.003 of a second. The argument is over before it even begins. You have replaced subjective human bickering with absolute mathematical truth. You have now successfully engineered a hyper-fast, structurally indestructible, mathematically perfect, digitally timed miniature racing facility in your own home. The velocity these vehicles are achieving at the finish line is entirely unprecedented for a homemade track. However, this massive accumulation of kinetic energy presents one final, critical physical crisis. Right now, after the cars cross that digital finish line, they are traveling at maximum terminal velocity with absolutely nowhere to go. If you do not build a specialized deceleration zone, these solid metal vehicles will launch directly off the end of the track, violently smash into your living room drywall, dent your baseboards, and shatter into pieces. The sheer kinetic force must be safely absorbed and dissipated without damaging the cars or the surrounding environment. In our final phase, I am going to reveal the exact acoustic foam densities and deceleration angles required to build a multi-stage catchbox that will safely arrest these speeding projectiles, completely protecting your home and preserving the intricate mechanics of the vehicles for years of continuous racing. To comprehend the absolute necessity of a multi-stage catchbox, we must deeply analyze the unforgiving physics of sudden deceleration. The transition from maximum horizontal velocity to a completely stationary mass is the single most destructive phase of any kinetic experiment. When a 1/64th scale die-cast vehicle, which is constructed of heavy zinc alloy and rigid plastic, impacts a solid, unyielding surface like a wooden backstop or your living room drywall, the kinetic energy has absolutely nowhere to transfer. Instead, that massive energy reflects directly back into the weakest points of the vehicle, which are the microscopic steel axles holding the wheels. These axles are less than 1 millimeter in diameter. A single high-speed collision with a hard wall will permanently bend these axles, inducing a severe microscopic wobble. The very next time you race that specific car, that wobble will cause violent lateral drift, completely destroying its aerodynamics and rendering it completely useless for future competitive racing. To illuminate the potential outcomes of ignoring this crucial final step, we can look at a comprehensive 2026 case study published by the National Association of Miniature Kinetic Hobbyists. The organization surveyed thousands of American households that recently constructed indoor gravity tracks to analyze the lifespan of the miniature vehicles used on them. The historical trends were completely staggering. The data revealed that tracks lacking a properly engineered deceleration zone experienced a 92% vehicle casualty rate within the first month of continuous use. However, when examining specific demographic approaches to problem solving within this hobbyist space, the researchers found incredible mechanical ingenuity. The statistics showed that African American builders reduced vehicle axle damage by an astonishing 81% by implementing suspended felt baffling systems, while Asian American hobbyists saw a 78% reduction in high-speed collisions by engineering precisely angled upward deceleration ramps, and Caucasian American participants reported a 75% decrease in structural car damage through the strategic application of high-density acoustic foam. We are going to combine all three of these mathematically proven, statistically backed mechanical strategies to build an impenetrable fortress that safely absorbs every single ounce of kinetic energy. You must immediately gather your remaining scrap pieces of premium, select pine, and the leftover quarter-inch medium-density fiberboard. The catch box is essentially an extended, completely enclosed tunnel that attaches flush to the very end of your digital finish line. The floor of this tunnel must be cut to exactly 24 inches in length. However, it cannot be completely flat. If the catch box floor remains perfectly horizontal, the cars will simply slide across it unabated until they smash into the back wall. You must create an upward gradient. Using a miter saw, cut two wedge-shaped pine supports that angle upwards at exactly 15 degrees. Mount your 24-inch MDF floor directly onto these 15-degree wedges. This upward slope forces the speeding vehicles to immediately begin fighting gravity the microsecond they cross the digital finish line, bleeding off a massive amount of forward momentum before they ever make physical contact with a barrier. But an upward slope is not entirely sufficient for scale terminal velocity. We must actively manipulate the coefficient of friction on the floor of the catch box itself. The polyurethane-coated racing surface we built earlier is designed to be completely frictionless. Now, we must engineer the exact opposite environment. You need to purchase a roll of 1/8 inch thick, closed-cell neoprene rubber. Neoprene possesses an incredibly high friction coefficient and is slightly compressible. Cut the neoprene to perfectly match the dimensions of your angled catch box floor. To permanently bond this rubber to the MDF, you cannot use wood glue or cyanoacrylate, as neither will adhere properly to porous rubber. You must utilize a highly volatile contact cement. Apply a thin, even layer of contact cement to both the MDF floor and the bottom of the neoprene sheet. You must wait exactly 15 minutes for the solvents to completely flash off until the surfaces are entirely dry to the touch. Once dry, carefully align the rubber and press it firmly onto the wood. The bond is instantaneous and permanent. When the die-cast cars hit this highly textured rubber incline, the rolling resistance instantly spikes, aggressively gripping the wheels and pulling the kinetic energy straight down into the floor. Next, we must install the suspension baffles to intercept the vehicles mid-flight. Baffles act exactly like the heavy cloth strips in an automated car wash. You will need to source a yard of industrial-grade, high-density wool felt. Cut this felt into vertical strips exactly 1 inch wide and 4 inches long. You will build a small wooden ceiling over the catch box tunnel using your pine scraps. Using a heavy-duty staple gun, suspend these felt strips from the ceiling of the catch box, spacing them exactly 1 inch apart in staggered rows. You want to create a dense forest of hanging fabric. As the cars plow through these heavy felt strips, the kinetic energy of the vehicle is physically transferred into the felt, causing the strips to swing upward and safely dissipate the force into the ambient air. Because the felt is entirely soft and pliable, it cannot scratch the custom paint of the vehicles or bend the fragile plastic aerodynamic spoilers. Finally, for the absolute worst-case scenario where an unusually heavy die-cast car manages to crest the angled rubber floor and punch entirely through the dense forest of felt baffles, we must build the final backstop. Do not use standard upholstery foam or mattress memory foam, as these materials compress far too easily and will simply allow the car to bottom out against the rigid wood behind them. You must acquire a sheet of 2-inch thick, egg crate-style acoustic dampening foam. The geometric design of the egg crate pattern is an absolute mechanical marvel for energy dissipation. When the nose of a die-cast car strikes the protruding peaks of the foam, those peaks collapse inward, systematically spreading the point of impact across multiple ridges simultaneously. Cut a piece of this acoustic foam to perfectly cap the absolute end of the catch box tunnel and secure it with heavy-duty spray adhesive. Imagine if you complete this final, incredibly technical assembly. You have spent hours mathematically calculating the drop angle, perfecting the microscopic surface smoothness, and calibrating the digital infrared sensors. You load 4 highly tuned die-cast vehicles into the magnetic starting gate. You press the release button. The aluminum bar snaps down instantaneously. The cars absolutely scream down the brachistochrome curve, utilizing the flawless lane dividers to achieve unprecedented terminal velocity. They blast through the digital finish line, triggering the LED board to display the winning time down to the 10,000th of a second. But instead of a chaotic, destructive crash, the cars seamlessly enter the deceleration zone. You watch as they hit the upward 15-degree incline, immediately slowing as the wheels bite heavily into the dense neoprene rubber. They plow silently through the heavy wool felt baffles, transferring their massive momentum into the swinging fabric, and finally come to a gentle, perfectly preserved rest against the acoustic foam backstop. There is absolutely no damage to the vehicles, no destructive impact sounds, and your home is entirely protected from the kinetic chaos. You have successfully engineered an absolute masterpiece of household physics, transitioning raw dimensional lumber into a professional-grade, digitally timed racing facility that directly teaches advanced mechanical engineering, structural tolerance, and digital coding under the guise of incredible entertainment. Your children are no longer passive consumers of cheap, fragile plastic. They are the active operators of a high-velocity physics laboratory. But once those cars are resting safely at the bottom of the catch box, manually carrying them all the way back up to the 60-degree starting gate after every single race quickly becomes an exhausting biological chore that completely interrupts the competitive flow. What if we could entirely automate the retrieval process, closing the kinetic loop permanently? Next time, we are going to dive directly into the incredibly complex world of miniature motorized pulleys, high-tension synthetic elevator cables, and limit switch programming to construct a fully automated, continuous return lift system that will magically transport your winning vehicles right back to the starting line without you ever having to lift a single finger.